We have a capacitor being charged, in the process of being charged, so assume that at some point the charge is Q. The question is how much energy is required to move a small additional charge, delta Q. Now, I should probably say transfer an additional charge, delta Q. I think transfer is a better verb to use because, of course, essentially what we're doing, no matter how we do it, whether we pick it up with a pair of tweezers and move it over, or one way or another, transfer the charge, we're transferring charge from one plate to another. Okay, how much energy is required? How much work has to be done on that charge? Well, concepts. When we think of capacitance, it's just charge per volt. Okay, so that isn't directly related to energy, is it? But a volt is directly related to energy. Okay, a volt is energy per unit of charge. Okay, so capacitance is charge per volt, and the volts measure energy per unit of charge. Well, the energy transfer then is going to be the voltage times the charge that's being transferred. So the energy contribution, which I'm calling delta energy, is your charge that's being transferred, the delta Q, times the voltage. What voltage? Well, the voltage across the capacitor, because that's a voltage change, that's the potential change, whatever's causing it, between one plate and the other. And that's going to be then what? The voltage across the capacitor is Q over C. So the charge divided by the capacitance is equal to the voltage because the capacitance is equal to the charge divided by the voltage. I just rearranged this relationship to get this, which is less intuitive than this. Okay, so voltage across the capacitor is Q over C. The change in energy is delta Q times voltage, so the change in energy, delta Q times voltage, which is delta Q times the voltage, which is Q over C. Now I call that a delta U because that's a change in potential energy. You're moving the charge against an electric field, and you're doing work. Now, I'm being a little bit careless with signs. Okay, if the work you're doing is delta Q times Q over C, change potential energy to be negative, well, you got to be a little more careful about how you assign pluses and minuses in this situation. So we're not going to, I don't want to digress to that. You do want to think about that, and you do want to see how your textbook derives that, but I don't want to talk about that. I want to just go pretty directly to the result here. So, well, there are many ways to think about this. Let's say we go from voltage 0 to the voltage of our source with this system. Okay, then the charge is going to go from what? 0 to capacitance times source voltage. The capacitor will cease charging when its voltage is equal and opposite to the source voltage. And that equal and opposite thing helps reconcile the signs of our potential energy and our work and so forth. Well, your sum of all the delta U contributions of all the little charges that get transferred, well, the total change of potential energy to go from here to here is the sum of all the contributions of small charges that are transferred. And remember, every small charge is being transferred against an increasing capacitor charge, so it's being transferred against an increasing voltage. Now, the introductory problem sets make it clear how that works. So I'm not going to say, except to say that, you know, if you start with no charge, transfer a little bit of charge, you get a little bit of voltage. So now the next charge has to fight that voltage. Okay, so the next charge is fighting a little more voltage, and that increases the voltage when that's transferred, so the next charge after that goes against a greater voltage. Okay, well, you add up all those Q over C delta Q's, And you take the limit, and that approaches the integral Q over C dQ in a way that I hope you understand more deeply than you did when you took your calculus courses. Because, of course, you need to keep understanding this more deeply, and most people don't understand it all that deeply. They learn to do it and so forth. I hope that you're applying it and thinking back to what you learned in calculus and reconciling it with the physics. Okay, well, and I can only do so much. I can talk about it, but you have to do it. Okay, well, this is going to then be an integral, and it's going to be the integral as Q goes from 0 to the maximum charge, which is 0 to C V sub S. Now, C V sub S could be written as Q max. So instead of CVS here, I could have Q max. Well, it's obviously antiderivative of Q dQ is 1/2 Q squared. You still have the C in the denominator, so you're going to get 1/2 Q squared over C, or if you wish, Q squared over 2C. Then you substitute the limits in. Well, you get 0 here because you're substituting 0 for Q. And you get either CVS for your max charge, or I'll use Q max for the max charge. And that's the same as 1/2 CVS quantity squared over C, which is 1/2 C times VS squared, because Q max is CVS. And this is all very intuitive, and you check out the units. Capacitance is what? Charge per unit of voltage, okay? Charge per volt. This is squared volts, so you get charge times volts, and charge times volts, since a volt is energy per unit of charge, gives you units of energy. So this is an energy, and it is your energy of the capacitor. Well, expressing it in this form, which is a more common form, because in general you're not thinking just in terms of this circuit, you get Q squared over 2C. That's the energy stored in a capacitor, and since the electrical field against which you transfer the charge is a conservative field, this is a change in potential energy. Again, I've been a little careless about the plus and the minus, okay? Then if you want to reconcile the plus and the minus, actually you're moving the charge against the opposite, a voltage that's in the opposite direction, has an opposite sign to the charge that you're moving. So the work you're doing is negative, and the change in potential energy being equal and opposite to the work done by the conservative force is therefore positive. So you do have this sign. Now, I want you to think through that, though. Okay, that's the potential energy stored by a capacitor. If you got a capacitor with charge Q on it, then the energy it stores is Q squared over 2C. And you can kind of think of that energy as being stored in the field of the capacitor, the field between the two plates. And hopefully we'll be able to develop that idea a little further, but that's as far as we're going to go for right now.